This morning it's a pleasure to welcome Jose Carrillo from Imperial College London, and Jose is going to be talking about swarming models with repulsive attractive effects, pattern stability. Jose.
Thank you very much, Mark, for the presentation. Thanks the organizers for the invitation here. My talk is, as the title says, is related to swarming models. They are individual-based models, very similar to the ones that are used in cell or organogenesis, and they have been discussed in several of the talks before. But I will concentrate mainly on what are the basic mechanisms that trigger some of the patterns that we see in these swarming models, rather in the application of these directly to real situations. So my interest more goes into the direction of trying to understand the implications of some of the rules that we assume of interaction between the individuals. So the first part is about kind of a survey or a kind of a quick overview of some of the models that people have been using for modeling this group behavior. And then later I will concentrate in part of it, studying some properties of stability of these coherent structures and some particular solutions that we call flux solutions. You will see why I call them like this. And finally, I will briefly discuss how to connect to PD models and what are the interesting open questions in that direction too. So, about these collective behavior models. So many pictures already give you an idea of the kind of thing that you would like to reproduce or at least try to explain. So in many different situations, say for these ones that we have in the slide, fish schools or bird flocks, you have this formation of large coherent structures that you see in life and in many TV documentaries. I mean, you just go to Google and do BBC swarm, you will find plenty of interesting documentaries about it. And in some of them you see, well, these kind of swift movements, but coherent, keeping the structure of a large group of individuals without seemingly the existence, say, of a leader in the group that decides for everybody what they should do. Okay, I'm not going to show you the movies because I'm sure you have seen plenty of them. But you see here some of these structures which are quite nice, like this kind of rolling movement or mill movement around certain location, and the kind of flock behavior for birds. Okay, so what are the basic mechanisms, some of the basic mechanisms that have been considered to be important in order to model this kind of movement? So plenty of people, they have introduced essentially models based on three basic rules: inner repulsion, some way of attraction between the individuals, and some way of alignment between individuals. So of course the details are in how you incorporate these three basic mechanisms, but essentially everybody agrees that these three basic mechanisms are somehow the basic ideas that you have to incorporate into the model in order to have something coherent for the movement, I mean, for the formation of this kind of patterns. So there is a lot of discussion in the theoretical biology community and the applied math community about how to impose this. I'm not going to enter into if interactions should be by the distance or interactions should be by the topology, but this is part of the interest there also to discriminate between one or the other type of interaction or the importance in different species. I'm going to present you, in fact, two very basic models, which are totally unrealistic, but that they contain the minimal ingredients that lead to the formation of some patterns. And my idea more is in the direction, as I said, of trying to explain why this happens in some of these models, with the idea that in more complicated models, some of the basic phenomena that we discover here will anyhow hold. So there is one model that was introduced by the group working in this at UCLA, and Andrea Bertozzi, Lincoln Chase, Maria Rita Dorsonia, and collaborators. It's a very basic model in which you introduce this inner repulsion and long-range attraction effect by a kind of a social force, a kind of effective potential. So assume there is a potential of interaction between the individuals, so in somehow you are treating the particles as point particles interacting with through a potential. That's why I have Newton, that we always have to have it present anyhow. And I assume that there is a kind of inner repulsion for me with the choice of sign that I have here for if I assume that the potential is radial, decreasing means that it's repulsive, increasing means that it's attractive. Okay? And apart from this potential interaction between the individuals, the other mechanism that I am considering here is this term, and the role of that term is just to fix a cruise speed for the individuals. So the idea is that you are only interested in what happens when the individuals, when they travel at a certain speed. You are not interested when they are when they stop somewhere. So then you fix asymptotically that the individuals will move with certain speed, which is the square root of alpha over beta. Just to keep in mind some particular sample of potential, so think about a potential which is a combination of two exponential decaying functions of the radii. This is what is called a Morse potential. So choosing the constants there and the length scales in the right way, which is like that, you obtain a potential with that shape, which is biologically reasonable in the sense that it's repulsive for a short distance and attractive to a long distance, and it fixes some kind of typical interaction length between two particles. You can cook up many of these potentials anyhow with different shapes and properties at zero. So, so this is a very basic model, but you will see that from the point of view of the time, the evolution of a random set of initial data is quite interesting. Let me just mention also that there is no alignment mechanism directly included here in the model. Only you have attraction, repulsion, and the fixed speed term. Okay. Nevertheless, some of the patterns that you see, and I will put this to run in just a sec. So let's start with this too. So let's let's concentrate our attention here in this window. In all the simulations, I fix the center of mass as the origin. Okay, so the window will be moving really, and you see here that after a while, the particles, they just reorganize into certain shape, certain particular shape in the space, and they just move translationally in certain direction. So they arrive to a consensus in velocity in the direction without imposing a priori any mechanism to do that.
Sorry, is this 2D or a projection of 3D?
It's 2D. Everything is 2D here. I will show one in 3D.
Another
So,
break, another X-ray. And the direction depends on the initial condition, right? So if
Yeah,
you
sure,
change the initial,
sure.
go this way.
Sure. The direction depends on the initial condition. Oh yeah, okay. So while I was talking, you see, we waited a bit, and there it seemed that there was nothing. It was quite random, but in fact, at the end, you arrive to one of the other patterns that you see, which is called the mill pattern. That's the one in which somehow the particles arrange rolling around certain location. As I said, the center of mass will be moving, okay? So this, you arrive to a certain location and then they start rolling around. And these two patterns may happen with the same value of the parameters. It depends on the initial condition. So that's somehow the surprising fact about this very simple model. You can have even more complicated things. And this one is for a certain range of the parameters, especially when the repulsion is not too strong. Then you can have that individuals, they roll around in two different mills, one clockwise and one anti-clockwise. And that's what is usually called the double mill. And it seems quite robust, at least for very long time simulations we did. Although we don't have a theoretical way of saying that it's a stable solution in some sense.
So are these independent of the potential?
No, this depends on the potential, of course. Most of the simulations I'm showing you here are for the Morse potential. Then it depends on the potential, the kind of things that you see, of course, crucially. I will discuss about it a bit.
You tried varying the proportion of which ones is flying counterclockwise and clockwise to see if transition?
Well, we didn't check that, but as I said before, it appears exactly when the repulsion is not too strong. In that case, then they allow, I mean, they don't turn around immediately when they pass close to each other. No, we didn't check that. Okay, so two more simulations I wanted to show you. One in 3D. So probably you see a lot of flickering around. Sorry for that. Again, it's the same idea. It has been fixed in the center of mass, the origin of the window. I mean, the origin of the simulation. And you see that they rearrange in some kind of flock again, some kind of ball, a sphere shape, moving in certain direction. And then you have also this kind of rolling around in the axis of symmetry of the, let's say, kind of helicoidal movement of the particles, anyhow. So which is interesting. It appears always in 3D simulations. There is also asymmetric patterns in 3D. And so it's, I mean, it's quite rich from that point of view. You can, if you want, also introduce other kind of effects. For instance, here the additional effect that we included is that if the particles are very far away from the origin, there is a turning around force. Okay? So there is some force that wants that to come back to the origin. And then naturally you destroy the mills, and then typically what you get is this kind of a milling flock around certain location. So the interest of the model, as I said, is quite rich dynamically, and not clear how to study a priori stability of some of these stable patterns. I will tell you later on what we know. Then let me mention for a bit for completeness a model in which you have an alignment term. Again, this model is quite simple in spirit, probably quite unrealistic if you want to use it in math biology, but with other ingredients might be also applicable. And people are using it, in fact. I will discuss that in a sec. Okay, so here, how you introduce alignment in this model is to assume that every individual in the flock is able to measure its relative speed with any other individual. So that's a big assumption, because I'm assuming that instantaneously, let's say a bird is able to measure its relative velocity with anybody else. And then what they do is to average the relative velocity. So Vj minus Vi is average with certain weights, Aij. And the smart part here is that the Aij are going to depend on the interparticle distance, being the idea that those that are close to you count more for the average than those that are far from you. There are different ways of doing that. You can normalize the average, also is the same. There are several people that have worked on that, and well, in fact, this model was introduced by Felipe Cooker and Stephen Snail some years ago. And the interesting thing here, and that's why I call it velocity consensus model, is that under certain assumptions, so for instance, this gamma is less than 1/2, so if the tail, if the individuals, they feel each other strongly enough, then you arrive to a consensus in velocity no matter what the initial data is. Is what it means asymptotic flocking. But if the strength is not too big, in this case they assume it's algebraic decay, then what you have is the formation of clustering, and you can have a global consensus in velocity under certain assumptions on the initial data. So, somehow, if you put this together with the previous model, I mean, you could put both effects together, you destroy essentially the mill, you typically get just a flock. Okay, so this is about some of the simulations with these two basic models. Let me mention that out of these models you can write several first-order models, which in some way or another have appeared in some of the talks. So what I mean is that you work with the second order model, but you assume that inertia term is negligible. Let's make the simpler assumption that we have just a term that dumps that is standard damping in the velocity. So then you get to first order model in which you have only the interaction between the individuals through the pairwise repulsive attractive potential. And in fact, this is very similar to ideas that, for instance, were in the talk of Luigi Preziosi when he was talking about the zebra fish model for the formation of the spinal cord. Typically here, and this is my first connection to PDEs right now, I will come back to that later, you can write what is the continuum model for this first order PDE. I will come back to second order PDEs later on. And it's quite clear to see that you think about having a density of particles, given you how many particles you have at a certain location, and you want to write a continuum model for the evolution of that density of particles out of the system of m particles. What you expect to have is a continuity equation where the velocity field is non-locally computed from density during the convolution of gradient u, which is exactly the kind of model that Luigi was discussing with two species. What is the connection between this one and the second order model that I introduced at the beginning? So the connection, you can see it right now, a bit naive, but you can see from the point of view of just finding particular solutions. So let's concentrate on what I call the flux solution. The flux solution was this solution in which all the particles are arranged in certain interparticle distances and they just move translationally. So can we find the shape depending on the potential, as Anotida was asking me before? So let's do the very simple computation of finding solutions of this form for the second order model of Bertozzi and company. So which are certain positions that I'm going to call XIS, that has translationally moving with a velocity which is fixed of the right modulus, square root of alpha over beta. So we come back to the equations that I don't have in this slide, sorry for this. Let's do that. Since the velocities are all of the same modulus, this is 0. So if you're looking for something which is steady, it should be 0, so the sum of forces should be 0. And then you will have the corresponding shape. So this just to say that then these XIS, what they are just a steady state, discrete steady state, if you want, of this kind of problem. So the positions will be just a steady state of the first order model, and if you think in terms of the continuum model, you will be thinking of the steady states for this equation if you have a large number of particles. So now we arrived also to an interesting question here. For which potentials do we get towards non-trivial steady states for an equation like that? And once we have those steady states, is there any implication of the stability of those for the first order model to the second order model? Because they look completely different a priori in terms of the dynamics. Okay, let me mention here also a little connection to nonlinear diffusion models at the level of the diffusion equation. I mean, it's a connection that many people also in the audience know, which is the fact that you can model always repulsion by a kind of porous medium term, because it's like you can connect it to the non-local model, because it's just assuming that the repulsion is very strong. You assume the repulsion is given by essentially a Dirac at 0, then formally, if you put it over here, you separate it into two pieces. The attractive part of the potential, you keep it non-local. The repulsive part, you just put it there, and you will get the gradient, obviously, you put it on the row. So you have Dirac convolution gradient rho, you get gradient rho times rho, Laplace rho squared set constants. Okay? So essentially, the porous medium kind of term is a very strong repulsion. You can think about it in those terms. Okay, so yeah, it's Friday morning after a long week, so we continue with the fun. and simulations. So let me show you now simulations for the first order model. Again, they are just discrete simulations, so I'm just doing the gradient flow of the first order model. So what I mean is that I just look at, I just do a steepest descent of this set of ODs, and I say a steepest descent because this has the structure of a gradient flow of certain energy, which is the total interaction energy. So this is how I produce these simulations here. And I will tell you which potential I'm using in each of them, but let me let's just have a look at the simulations first. So in these two, you see this very quick, fast movement of the particles towards a kind of circle of certain radius. And here, it seems people are not happy in the sense of when they get to the circle, at some point, some instability triggers, and then the particles, they just aggregate around in certain locations. While if you do a zoom here, what is happening with the particles, there's the same number of particles, more or less 200. What happens is that the particles are just rearranging themselves to equal distances on certain cycle. Okay? Yeah, here we have other two simulations. The first one, again, you have this fast tendency to the circle, but then again they are not happy for some different reason. There is some instability in the shape. It gets a bit triangular shape, and then the particles arrange into certain pieces of curve. And here we saw that tendency to get towards the boundary of the of certain circle, but I mean there is a graduation in the density when we go there. And in fact, the fact that there is a gap here is not so clear because it depends on how much mass you put in each of the particles when you do the simulation. So this is just with fixed number. So let me tell you first which potential I was using here. The interest is that I was using of those simulations is that I was using a potential which is very, very, very simple. It's just a combination of two powers. So it's a power law potential in which I have A larger than B means that it's attractive at infinity and repulsive at 0. B is controlling the repulsion at 0. And the only thing I was doing in the simulation is fixing A, moving B. So in the first simulation, B was larger than 2. So the potential is smooth enough at 0. So C2 derivatives at 0. And typically have the concentration on 2 points. While if I get a potential which is more and more repulsive, as the potential gets more and more repulsive at 0, so this means that I decrease the B. Then at some point I see that the particles, they prefer to rearrange into some curve, in that case a circle, and then the circle is not the preferred shape, it thickens, and then it tries to distribute over a whole ball. So this is essentially when B is very close to 0, this is into D, and B close to 0 means essentially close to Newtonian, because B going to 0 is like the log in that case, which is Newtonian in 2D. Okay, so the moral of the story is that the shape of the stationary state that you see is going to depend crucially on the repulsion at 0. As the repulsion gets stronger and stronger, you see that the set in which the particles concentrate gets larger and larger. And one can prove some theorems about that, even if today I'm not going to discuss about this. So all the modeling you want is done at the level of the potential, and if you just play around with a bit more complicated potentials, you can have a lot of fun. And for instance, you can have things like that. And it's not too fancy potential, it's just constructed with a hyperbolic arcotangent of some kind. I mean, not too fancy. Anyhow, it's linear at 0, the repulsion here. And well, so you get shapes like this. Okay. I usually say that you should do, this is like a psychological test. You should tell me what you see in that one. Yeah, I don't know.
Have you managed to achieve anything that's other than threefold symmetry?
The symmetry, you can see other symmetries, yeah. And this depends crucially on the potential too. For the power law, you never see, I mean, the threefold symmetry is the only symmetry you see for the power law potential. Because you can study carefully the instabilities of the some particular stationary state, which is, in fact, is not is clear now from the simulations that it seems that a good candidate to be a stationary state is the uniform distribution on a circle. You can show that this is the case. It's always a stationary state. Sometimes it's stable, sometimes it's not. And you can see by doing linear stability analysis of the uniform distribution on a circle that the first instability that may happen is the threefold symmetry instability. But there are other potentials in which you can see fivefold, sevenfold, and you can cook up also vice versa. There are people that have been studied the inverse problem. So I want to have some shape. What is the potential that gives me some shape with certain number of symmetries? Okay? So these people have done. There is no full answer to that inverse problem because it's very complicated, but there are some partial answers. So it's quite rich, even the shape of the stationary states, as you see, depending on the potential. So this is also one of the interests of the models here. What else I wanted to say? Yeah. Okay. So now I'm going to come back to the connection to the what information do we get from the first order model to the second order model. In principle, we just saw this simple connection that steady states, those steady states that you have seen for the simulations of the first order model are steady states for the second order model. But apart from that, can I get some other information about the dynamics, for instance? And this is something that we have worked in terms of the stability of the flock pattern. So let me briefly mention some of the results that we got here. I don't know how far I will go into some details, but probably not. So let's just concentrate on the second order model, either the one by the UCLA group or that one plus the term of Cooker-Smale type that I write in this way, where you want to have something in mind. Let's assume the potential is the power law potential, for instance. Could be done with the Morse potential, it doesn't really matter. And the term for the average for the alignment, let's assume that it's also like an algebraic function of the interparticle distance as in the original model of Cooker and Smale. Okay, in each of these two, if you take a stationary state of the first order model for that given potential, you plug it in here and you choose one velocity direction. That's a flux solution of this model. So now the question is, what can we say about the stability of the flux solution? The first thing that comes to your mind, if you have a large system, even if you have a large system of all these, is to do linear stability analysis. So let's see what do we get by linear stability analysis. This is just to have something in mind. You have the, as I said, the uniform distribution on a certain circle is always a stationary state. And then you can look at the particular case of stabilities or instabilities of that particular case because it's very explicit and you can do plenty of computations. But you can do it with any stationary state, okay? And that's the thing I want to present. In fact, the stability of that particular solution was done by the UCLA group. So let me start with instabilities. The first thing that comes to your mind, since it's a moving solution, it's a time-dependent solution, let's see, let's do a change of variables and let's do and make it steady. This one is very simple here because it's just moving translationally, so you just go to the comoving frame, okay? So you get to those variables and linearize around now the stationary state. So you do the linearization and just here this linearization is written for the uniform distribution of the circle, but yeah, let's forget about that. It can be done in general. It's not that important. So you do linearization around certain steady state for the first of the model given by positions x, j hat. Okay, so the linearized matrix that you get is a 2n, well, 2n by 2n matrix, but it has some structure, and that's the interesting thing. From x dot equals v, you get this big block of zeros and this big block of identity. And from the second equation, so from the interaction force, you get this matrix M, which is symmetric, and it's given in terms of the Hessian of the potential at the interparticle distances. And the interesting thing is that that matrix is precisely the linearized matrix around the steady state of the first order model. So the interesting thing is that the structure has precisely one of the blocks is exactly the linearization of the first order model. And then you have this other block, and this other block is formed by 2 by 2 matrices. It's a kind of diagonal matrix of 2 by 2 blocks given by the direction where you are moving. Transpose U0 is the direction you are moving. For instance, you can assume always is 1, 0, so they are blocks of 1, 0, 0, 0, n blocks of those, times the factor minus 2b, beta. Beta is the term that appears in that fixes the cruise speed of the individuals, and the thing is that that term is crucial, okay? The presence of that term is crucial because it's mixing the information somehow from the x to the v. So in fact, what we learned first is kind of negative result. You can always check that if you do these change variables I told you, just moving frame, then you destroy one symmetry of the system because of the its translational invariant, rotational invariant, and then you get always a non-trivial, so you get always a generalized eigenvector associated to the 0 eigenvalue. So that's bad news if you want to do the linear stability analysis, because it will be always linearly unstable. But nevertheless, what you learn is something about instabilities. And that's one of the first surprises here, that you can relate the whole eigenvalues of the second order model to the first order model in the following sense. You can show that there is an eigenvalue with positive real part of this linearized matrix, zero identity m minus 2 beta u, if and only if the linearized first order system has a positive eigenvalue. And I just said positive eigenvalue because that one is symmetric. So this tells you, in other words, that the stationary solution is unstable for the first order model if and only if, almost, is unstable for the second order model. And the interesting thing is that if and only if. So, I mean, that was a surprise for us because we thought, okay, well, I mean, from the first order model, well, we learned for the second order model that looks like a Hamiltonian except that term with a beta. So in fact, you learn a lot, and well, so you get that surprise. And so we thought maybe then the stability the stability result may be true. I cannot study the stability from here because of the the generalized eigenvector associated to the 0 eigenvalue. And then what we realized is that in fact, in the dynamical system, they have a general theory when you have certain symmetries, that what you can do is to study the stability not of a single solution, but rather of a family of solutions. And we thought, okay, let's try to see if we can use that theory in our case. And in order to do that, I will spare you with the details. By the way, before showing you that different approach, this is numerical simulation confirmation of the instabilities. Yes, I use the same potentials and in the first order model with the same with the perturbation of the initial data. So what is done here is a stationary state at the beginning is just the uniform distribution on the ring. I do a small perturbation, and then I see what happens. In that case, it's stable, and in the other 3 cases, it's unstable, and then you end up in another stationary state. And that was exactly what that analysis was giving us. Okay? So this is just by looking at the linear stability analysis of the uniform distribution on the circle. I repeat again, that one gives you stability. I mean, gives you stability. Linear stability analysis doesn't give you anything. In these 3, it gives you that it's unstable. And that's you end up in a different thing, in a different stationary state. Okay. So, but what can we do for stability? So in fact, as I was saying, what we have to do is to study the system in a different set of variables. So with a different change of variables. We cannot just single out one single flock and do the change of variables to the comoving frame. The idea is very simple. If you do that, you will be naturally always unstable. Why? Because if you just take out the velocity of one single flock, a nearby flock that is moving in a slightly different direction will always separate from that one. So it's natural, it's clear that it's going to be unstable because you can perturb a little bit the velocity and you will end up in another flock moving in a different direction, so it will separate. So the idea is that you have to change variables with something that makes all flock solutions at the same time steady. How to do that? That looks a bit impossible, so it's very easy again. The idea is to change variables but with the mean velocity of the solution. So you just compute the mean velocity of the solution and you do the change of variables with the mean velocity. And I'm going to spare you with all the computations, but the thing is that in this way you can write an equivalent system of all these. You can reduce your dynamics because you added 2 additional variables, but you can reduce dynamics to an invariant subset of the right dimension, study the stability analysis in that invariant subset, and then finally, after some pages of computation, then you get this kind of result, which says the following. Essentially, you give me one steady state of the first order model, and let's take the set of solutions corresponding, all the set of flock solutions corresponding to that steady state, moving in any direction. Then that set is stable in the following sense. You take a flock solution and you do a small perturbation of the flock solution. After some time, it will come back to be a flock solution, but move in a slightly different direction. That is what it means, this kind of stability of the whole family of flocks. So if from that sense, in that sense, the set of flock solutions is stable if the shape of the steady state is stable for the first order model. So again, a surprise, the stability of the first order model implies the stability of the flock solutions for the second order model. So that's the kind of result that you get also. Okay, so what else I wanted to say? Yes. Now I want to move to the connection to continuum models. How you go to continuum models and what do you gain going to continuum models from the point of view of the application? If you want to study any of the stability properties for the shapes of the patterns that you see. Well, first, let's go to a continuum model. This already appeared in some of the talks. The procedure to a continuum model is through what is called the mean field limit. At least I think it appeared in the talk of Pierre, but I'm sure it appeared also in some other talk. What you do is associated to your dynamical system, you write what is called the empirical measure. The empirical measure associated to the dynamical system is a probability density that tells you that with probability 1 you will be at the location of the particle. That's why you have a Dirac delta at xit vit, and 0 otherwise. And well, if we put all particles equal, the MIs will be 1 over the number of particles. If they are different, so you can just play with different masses if you want. And the question is that you define that associated to your preferred dynamical system with the effects you want. So say you have all the effects. And then the game is to look at the limit when the number of particles goes to infinity of the empirical measure. Can you prove that the Fn as n goes to infinity satisfies something, satisfies some PDE? In fact, for the first order model that I wrote at the beginning, you have exactly the same procedure. In that case, we just develop it, or we obtain that non-local velocity field just by mimicking what was done at the discrete level. But you can do it also, you can think about it in this perspective. So here, the math viewpoint of trying to prove something enters into what are the assumptions that you need on the potential or on the weights in such a way that you can pass to the limit. Anyhow, you can always do a BBGKY hierarchy approach, like what Pierre was discussing yesterday, and get what are the continuum models. What are the continuum models typically you get by this procedure for the second order model? What you get are Blasov-like equations. So in the particular case of the model by Bertozzi and company, what you get is this kind of Blasov equation where you have this nonlinearity, again, non-local term, gradient of the potential combined with rho. What is rho here? Rho is the macroscopic density associated to F, so it means the integral of F in dV. So it's the density, the macroscopic density in a space. And this is just to show you a bit the other case when you have the alignment or when you have both. Essentially, you recover some non-local, always some kind of non-local term. In the case of alignment, you have a double kind of double convolution in this case, both in velocity and in space. So, okay, you can do that. But now the question from the applied mathematician viewpoint is, what have we gained with this? We went from a very large system of ODs to an evolution equation in 6 dimensions if we're in R3. So it looks like a crazy gaming, okay? Nevertheless, the idea is that, as usual, kinetic theory might be helpful in bridging between the ODs, the particles, and some more macroscopic description in terms of average quantities. So what you want to do is just to take it as a middle ground. So, in fact, in this particular case, we don't have any noise, we don't have any randomness, so we don't have a dissipation built in the system. So it's more complicated to do, certainly it's very complicated to do rigorously a passage to a kind of macroscopic equations. Nevertheless, you can compute some particular solutions of that, with some associated macroscopic equations. How to do this? So, to do this, what you do is to look for particular solutions of your kinetic PDE. What you do is you look for solutions with the following ansatz. The ansatz means that at each location, at each time, there is only one preferred velocity. So that's why you look for a solution which is of the form a density, the macroscopic density, rho xt, and at that location you look for only one velocity, uxt, so that's why you have that the distribution in velocity is deterministic. It's a Dirac v minus u tx. So you do that, and you just put the ansatz in the weak formulation of the equation, look for the equations for rho and u. And what you get for rho and u is this coupled system of kind of hydrodynamic fluid mechanic equations. So you get the first one is continuity equation. The second one, you have the typical inertia term, so rho, material derivative of u respect to t. Here you have the non-local force, where you have repulsion and attraction. And here you have the term, that's what it has been done for the model by Bertozzi and company, you have the term that fixes the velocity, the speed of the particles. Okay? Good. So it looks like compressible Euler. But of course, in the audience, you really realize that there's some term that we are missing. It's not really compressible Euler because I don't have a pressure. Okay, there is no pressure directly. Some sense, there's no pressure, so you would think, okay, oh my God, pressureless Euler, it's going to be terrible. Yeah, well, looks like terrible. I agree. Nevertheless, let's see what you can do by simulations. Let's solve it. No. So this simulation is just a particle simulation. I showed it to you before already. So this particle simulation was done with an additional effect, which was the standing around force, in such a way that you have the milling flock and everything is confined. So there will be an additional force here, but it's just linear, okay? It's rho times a force that makes them to turn, so it's very easy to handle. And here, what I'm gonna show you is a numerical simulation of these equations with an initial data which is more or less supported on a ball nearby the origin, okay? So, we didn't make any effort in trying to make them with more or less the same initial condition or anything. Just qualitatively, this is my point. Just qualitatively, you see that you get a kind of milling flock in the problem in this kind of equation with the same, exactly the same ingredients. So what I'm showing you here is the density. The density becomes very concentrated in some region, almost zero. Vacuum outside, so yes, you have to deal with vacuum in an equation like that, which is not easy. And you see that, well, I mean, it's not exactly uniformly distributed, the density on that region, but nevertheless, it goes around. It has more or less the same qualitative behavior. So one should expect in such an equation to have problems in terms of regularity of solutions, because it's pressureless Euler, you could have blow up and things like that. In fact, we have studied this equation in one dimension with Eitan Tammor and a postdoc of mine, John Pilchoy. You have initial conditions for which you do have blow up here. But you also have, even in 1D, you can prove that you have conditions under which you have global existential solution. Not only that, this is not important in here, you converge as t goes to infinity to some shape. So it's quite interesting model in a sense, because it looks like, and that's the point in which I leave it, the discussion, it looks like this non-local term is acting as a pressure. In fact, you can think that the repulsive part of the potential should help you. The thing is that we don't know how much it helps. In the sense, I don't know how to get the repulsive part of the non-local term here and use it as a repulsion really in the system. Remember that in the case of the if you model the repulsion by a very strong repulsion, a Dirac, then this gives you gradient rho. Gradient rho times rho is gradient rho squared. You recover your pressure. So somehow the pressure is hidden in the repulsive part of that non-local term. And yeah, so let me just conclude. I think I hope I have convinced you that with very simple models involving these basic three mechanisms, you can have a lot of fun. And if you want to apply to real things, of course you have to include much more effects, but at least we have understood some of the particular ingredients in the model that trigger one effect or the other. We have understood the stability of flux. For mills, we don't know, and the situation for mills is much more complicated because it's a time-dependent problem where we cannot clearly reduce to some steady situation. And there is a very interesting question here about how stable are these patterns if you add noise. We have a very partial answer in some particular cases. And finally, I just want to thank all my collaborators in several papers that I have done in this business in the last 4 or 5 years. And thank you for your attention.
Tim.
A sort of double question, and 2 parts of which you can answer in whichever order you prefer. Is there data on any real organisms that suggests that our interaction can be, the principal interaction can be represented as a force derivable from a potential? That's part one. That's even neglecting the fact that in real life, most organisms, as you said at the beginning, you were neglecting, most organisms move in a fluid.
Yeah.
So how, the second part of the question is, how do the results you do show how do they get modified when you take a proper account of the dynamics of the fluids in which they are moving?
Okay, so first part of the question. So okay, data. So you have data for flocks of birds,
Which have nervous
starlings, which have been done by the Italian group around Giorgio Parisi. You know that maybe, and they suggest that the interaction is topological for birds, in the sense that they are nearest neighbor interaction. Instead of being given derived by a direct potential very non-local. Okay. Nevertheless, there are people working in the direction of trying to adjust, let's say, this model to starlings or fish, like the group in Groningen and Charlotte Hemmelrich, and they get very good agreement with certain species. So there are some discussion of, in that direction for instance, for birds. For fish. For fish, there is indication on the other direction, in fact, and that was given by Terrolas in Toulouse. The group of Terrolas have indication that, in fact, for fish it looks like a metric interaction is more important than topological interaction. So this, of course, is a discussion that you have to take into account all the information coming from the experiments and the real data that these theoretical biologists they have. So and we started to discuss with them, but we don't have access directly to the data. Nevertheless, as I said from the very beginning of my talk, the interest was just to pinpoint the ways of understanding the formation of some pattern or the other with this basic mechanism. Then the second part about the fluid. I was neglecting the interaction with the fluid. I think it was written somewhere in my slide.
You said it,
from the very beginning. You can include that, but then in which sense? You could include that just by adding another, like treating it like two-phase fluid or particles immersed in a fluid and with some drag force and so on. But I would say that the first order will be interested not to treat it as an active matter problem, in the sense that probably this problem you don't have to look at the very close interaction of two, let's say, particles we have certain shape like our flagella or things like that, because it's much less dense than that case. So yeah, but in principle you could do that by coupling with fluid equations and do some.
I wondered if you had sort of dragon.
We haven't done.
If somebody else like I've forgotten the name for the moment. If you put the fluid in, do these structures remain, or does the final
if you just
look quite different?
Yeah, if you just add drag force, essentially the flock patterns remain the same. This I haven't done directly, but people have studied this problem. Just let's say the particle system for the individuals in a fluid with just drag force, then a standard drag force, linear. Then they remain.
Can you observe? Is your model able to observe other dynamics which are not observed in nature?
Well, the basic models that I show you just these kind of patterns I described. No, I mean just the collective motion that you want in general.
Okay.
It will depend on the details that you put on each of the parts of the model. So as you see, it depends crucially also the shape, it depends crucially on the kind of potential you use and so on. So you can use the potential as a way of modeling there.
Passing to the macroscopic model, there is this kind of underlying assumption that the number of agents, particles, goes to infinity with respect to their size. How you cope with that?
Yeah, I probably went a bit fast there because there is an assumption in the mean-field limit. You assume that the interaction forces, the strength of the interaction forces decrease with the number of particles and n goes to infinity. So this factor 1/n that is in the sum of the particles is not only there because you want to normalize and have a probability density, but you are also assuming that the strength of each individual force between two individuals goes like 1/n. That's an assumption in the scaling. If you do different scalings, then you get different equations.
Luigi.
And what happens if you, because now you are summing over all the particles, right?
Hmm.
What happens if you assume that you are summing over some
Local.
local, say?
Locally. The thing is that, we don't know how to do a mean field limit like that. You tell me, let's just sum, but with some, let's say a fraction of the particles, or the particles around certain location. You can incorporate that partially, not at the level of the mean field limit, but at the level of the model by interaction regions, like what you had in your presentation.
You cut
Yes.
the
So
potential.
what you see, you incorporate it in the potential, you incorporate it in the alignment term, you incorporate sensory regions. For me here, the potential was just radial to simplify, but you could put it on a region, on a cone of vision, or a interaction region, call it like you want. This you can do, and you can do the mean field limit on top of that. This we have done recently. It's not so nice, because when you incorporate sensory regions, then your ODE becomes, your ODE system becomes very complicated, because somehow it's discontinuous at the right-hand side. At some point, you see, one particle could leave from the sensory region, then you have a force less, so it becomes, it's a system of ODs with this continuous right-hand side, so you have to be careful how to treat that. But it's doable. You can do the mean field limit, you get the same kind of Lasso-like equations. And if you do the first order, the overdamp limit, you end up in the same models that Andrea Tosin have been working for pedestrian flows, or for what he's doing with your group.
Okay, I think in the interest of keeping exactly on time, we'll leave the questions there. I'm sure Jose will answer any others during coffee and lunch. So just remains to thank Jose again for a lovely talk. Thank you.